All right. So is there anyone new here today who hasn't introduced themselves in one of these sessions? I know, Dror, you haven't been here for a while. Would you like to introduce yourself again?
Um, don't really remember how to introduce. I'm just another, I don't know, RChain fan, I guess.
Cool. Great. And you're in the UK now, right? So
Yes, yes.
cool. So and did I hear you were looking to like start up some sort of group over there for studying stuff? Was that something?
I said when I'm going back to Israel, I probably will try to
Ah,
start a community there. I
okay,
think
cool.
RChain Europe is planning to do some meetups around here, so
Okay, cool.
maybe I'll help them.
Awesome. Um, all right. And then I think everyone else has introduced themselves, but if anyone wants to, go ahead. All right. So yeah, first, just kicking things off, does anyone have any questions or anything that they're sort of hoping to discuss, pertaining to the second Introduction to the Design of Computational Calculi course that Greg gave last week?
I
And
was I was curious that he kind of offhand mentioned a implementation of SKI Combinator with poker chips that I thought sounded kind of cool. I thought about it a little bit, but I don't know if I totally got my head around how that would work. So if that
cool.
happens to come up, but I think that'd be cool.
Yeah, I don't quite know how that happened either, and I wasn't planning to look at the SKI calculus at all, but we could totally do that here. Awesome.
Yeah, maybe in the future I'll put a little more thought into it too.
Cool. Yeah. Yeah, I guess we'll get to other. Okay, so then let's just start going through stuff, and then if questions come up, then we can just answer them as they go. So I think the main thing that we were trying to grasp at in the last lecture was structural equivalences, which are just ways that we can erase the distinctions that exist in our grammar that we don't necessarily want to exist. So when we're writing down a program, when we're writing p par q, we want that to mean the same thing as q par p, right? We're just running these two things in parallel. When we're writing something down, a letter has to be before another letter, but we don't actually want that distinction to exist in our language. So you can think of structural equivalences as two-way rewrite rules. It's a way to take a program that has like a par with two things on either side and then switch the order of those things. And that once you've switched that order, you can also switch the order back again. So this is sort of to state the difference between structural equivalences and computational steps or reductions, which are also rewrite rules. We're rewriting the term of our program, is that our computational steps or reductions are a one-way transition, right? So, if you have these two processes, one sending and one receiving, and then another process executing after that, you can go from this term and you can rewrite it as just the term Q with whatever was sent being substituted for X in your program Q, and we can go that way just fine. But from this form, we can't necessarily take the step and go backwards this way. So one of the things that we talked about was alpha equivalence. So this means that two programs are the same. We can rename our variables without introducing any naming conflicts, and our program behaves the same. And we also went over bound names and free names in the lambda calculus. And with that, here's the lambda calculus grammar, and then here's the free name definition. And then we said that the name is bound if it occurs in the term but isn't free. So does anyone have any questions about this presentation? I know we did we had a digression into sort of what this notation means during that. And I wasn't really necessarily planning on going over all that again unless there were questions here.
I wanted to just clarify what I already think I know. Every name is either bound, XOR free, right? Not neither, not both. Every name that
yeah.
appears. Okay, cool.
So it's, yeah, every name that appears is either bound or free. It is sort of like contextually dependent, right? So in this like MN application, you could have a name that is bound in M, and then the same name is free in N, but in the process, M applied to N, the free name sort of overshadows the bound name, right? So it's sort of like you have your context dependent variable declarations there.
Yeah, got it. Good distinction. Thanks.
So yeah, just to, I guess, make sure that we understand this, we could give definitions of the names of a Lambda term in this presentation. Is that something that people would find useful? Otherwise, we could skip past that. All right, we'll skip past that. And I think that was outside of like the hands-on exercises stuff. I think that's mostly what was covered in last session. Yeah, were there any questions about any of that?
Hey, this is Rain here.
Hey.
So yeah, I think you're going to actually cover the notion of being bound or inside something or free in something today, right? So that may help that discussion as well. We talk about the ambient calculus and whatnot.
Yeah, yep. Yeah, so a couple of the hands-on things that Greg wanted us to work with were defining the domain equation and the Scala types for the grammar of the ambient process calculus, the blue calculus, and the linear lambda calculus. I think I've done the, or at least I've taken a crack at both the ambient and the blue calculus, but haven't started on the linear yet. And then also port the free name and bound name definitions into the Scala representation of our row calc grammar. So I guess now we could go over some different solutions for the free and bound name definitions, or we could go over the one that I wrote and the row calc grammar representation as well. Maybe we'll start there and then move into just like talking quickly about the ambient and blue calculus. Let's see. So can people read this? Is this big enough? Cool. Yeah, so here's my Scala definition of the row calc grammar. And yeah, one of the things that I was sort of a little bit unhappy about with this presentation is that when we're giving the mathematical definition, we have our type P, which is parametric in X, and then from that definition, we can sort of easily tie the recursive knot by saying our row process is equal to our P, that's parametric in X, of the type row process. And you sort of don't necessarily expose in that definition the construction of that second type of the name in quite the same way that you do in this Scala presentation. So I don't know if in Scala there's a way to take that parametric definition and sort of like close itself in like that. If if anyone has any pointers, that would be great. But what I ended up doing is just using two different traits, and this seems to work fine. But it seems a bit less than ideal to me.
What do you mean by two different traits?
So I have this type right here of process, and this type here that represents our name type. And the name type is constructed from the process type. That's the only way you can construct it. And then the process type is constructed in all of these ways. So people understand. Yeah.
Yeah, this is a side effect of Russell's paradox, right? Kind of.
Yeah. Yeah.
What's Russell's paradox?
I love how you assume that we all know what that is.
Some guy named Russell. No, it's, yeah, go ahead, Jake.
No, go for it.
Well, there's this chicken and egg problem always lurks around in the computer science world. It's not really a paradox in the classic sense, but when you just try to describe something inside itself, you're kind of caught here, actually a side effect of the language. So, because you're trying to do this in Scala, and so Scala has its own type system, if you will. So you're trying to almost, you know, describe something outside of Scala, but still be within Scala, kind of in a way. I mean, this is kind of a generalization, and that's, you know, so there's a notion of a not set out there. And it just doesn't express very well. It just gets confusing. So a big workaround people do is this kind of stuff, where you don't even try to get into that can of worms. You just say, look, there's a greater namespace, greater you know, set out there, trait or whatever you call it, and then you just narrow it down. So it's a long battle. It shows up in a lot of areas.
Yeah. Do you know if there's any the cats or Scala Z library like goes into any of that stuff or not? I just don't know.
Well, you can fight that battle, but the problem is, you know, you just move the problem a lot of times.
Right. Sorry, 1 second. Let me grab the dog. Hey, Willow. Come here. Come here. Hey, sit. Sit. All right, we'll see if that appeases her for now. Sorry for the barking. Yeah, so then I guess spoiler alert here, but here's a free name and bound name definition. This is how you do case class destructuring in Scala. You say, you know, you give me this thing that has a bunch of these case classes, and then we can match. And then the only way that you can construct a process P is, since this is a sealed trait, is all of these guys here. So if you have all of the cases here, then you have like a complete definition of what the free names and bound names are. So yeah, I think that's pretty straightforward from the definition. I guess you need to know that you know, in the drop operator that X is free. You need to know what the bound names and free names of the row calculus are, which are given in the row calculus paper here. Yeah. Anyone have any questions or things they'd like to discuss on that? Or should we go deeper into what these free and bound names are? Or yeah. Okay, so that, yeah, did anyone else take a crack at the free and bound name definition or the row calc grammar that that we should look at? I know, is Phil here right now? I know Phil took a crack at it. I think we'll probably not discuss that if he's not here, though. I don't know if he'd be cool with that. Okay, so then we can talk a little bit about the ambient calculus. Did anyone read any of the ambient calculus stuff?
I did not.
Okay, cool. So actually,
I read the wiki page, but I didn't find this document that you just showed there.
Yeah. I guess so. Yeah, we can go over a little bit about what an ambient is first. I think that'll help. So in the ambient process calculus, we have these entities that are called ambients, and they're essentially a bounded place where computation happens. So when they're thinking about these things logically, they're not thinking about threads or sort of like logical relations between processes, but what they're thinking of is, you have something like a web page, which is sort of constrained by the file of the web page, and that could be an ambient. Or you have a laptop computer, which has, computation can take place inside that laptop, but that laptop can, connect to a different network and sort of move around, or, a mobile phone or something. These are the sorts of entities that we're thinking about. An ambient can contain other ambients nested within each other. And an ambient can be moved, so it's taking a laptop out of a network connection, plugging into a new network connection. And an ambient can contain multiple processes running directly in the ambient controlling it. So you can have multiple sort of parallel things happening in the execution environment of the ambient. And then a name in the ambient calculus is something that can be created, passed around, used to name new ambients, and also having access to a name gives you like control into how you can interact with those ambients, which we'll see in a bit.
So when you talk about being passed around, like the ambients can communicate with each other?
Yes.
Are there restrictions on how that happens? Like, does it have to be the ones that are nested inside each other, or siblings, or how does that work?
Yeah, so we'll see that. It happens, within the confines of the language definition. And it's kind of interesting in that you can sort of use the ambient calculus to define communication, but the ambient calculus itself really doesn't have, at least in my interpretation, and maybe someone else has something different, but it doesn't really have the definition of like this communication. It just has this definition of like, I'm a process that directs an ambient, and I can interact with other ambients, and that like I can enter their environment, or I can enter my parent environment, or I can like spin off a new ambient that exists within my environment. That sort of interaction.
Okay, great.
Yeah, it's remember when you leave lambda calculus and go to the process calculus, it usually translates to some sort of a runtime, right, in the virtual machine. And so it's like going into a debugger. You can see names or whatever in the debugger, but they're not necessarily in the same structure, if you will, as the code that you defined it in, right? And whether or not you can see certain variables or not, there's this notion of reachability and all that kind of stuff. So just keep that in mind, that you're now considering the runtime container, if you will, where all this stuff lives. That's the biggest shift from lambda to getting to the higher order calculus.
Right, and it's different in that because there's like an interpretation of execution of lambda calculus where you have environments, right? But that's a different notion.
Yeah, because you could be doing non-lambda stuff too, right? There's a bunch of ways it can manifest itself. Contexts and all sorts of things that don't even have necessarily even a von Neumann interpretation, that kind of thing.
Are all names ambients and ambients names?
No. So names are used to reference ambients, and multiple ambients can be referenced by the same name.
By the same name? Multiple ambients can be referenced by the same name, or an ambient can have multiple names?
Both, I think.
Oh, wow. So
I don't know if I don't know if an ambient can have multiple names. That's
okay.
That I'm unclear of.
But multiple ambients can be referenced by the same name. So if I specify a name, that does not uniquely specify an ambient?
No, you sort of construct an ambient by saying this name, this, yeah, we'll look at the constructions here.
Okay,
That might
cool.
clear things up.
Okay.
Yeah, so the primitives of the mobility calculus is you have these set of n names, which are just sort of given. These are just kind of like our names in pi calculus. They just exist. And then we have our processes. So we have a restriction of a process, which is defining a new name that exists inside of that process that that doesn't exist anywhere else. Similar to the new construction in pi calculus. We have the zero processing activity, parallel composition, replication. Those all should be very familiar to us from the pi calculus. Where we start to diverge a little bit is where we say, here's how an ambient is constructed. So I give a name and then a process, and now this process is running inside of an ambient with that name. And then we have an action that we can take here. So there's these discrete actions that we can take before process P executes. So this is the same as like the pi.p representation in the pi calculus, where our pi could only be an input or an output, and they were blocking until they took place, and then p happened. A similar thing happens here, except these discrete actions that we can do are different than in the pi calculus. It's not a discrete communication. So the three things that we can do are titled in, out, and open, which we will reference in a little bit. And they're each given a name, and then something happens, and then that process runs. Is there a question? All right.
So it looks like in this calculus we don't get the concept that a name can be like a channel and we don't get that same, I don't know how to describe it, but that same sort of sublime kind of aspect of pi calculus, I guess, that you can a name can be both kind of data and the channel, and they can interact. One time it can be a channel, another time it can be a name or data. We don't get that same, I don't know how to describe it, but unless I'm missing it inside of here.
Yeah, I'm not so sure about that. Yeah, it really is like sort of in the pi calculus, what you're doing is passing around channels. And here you might be passing around names, but you're also passing around ambients and processes. So the things that you're passing around can be a little bit more complex than just a channel, which I think once we go into the in, out, and open operators, that might clear.
Okay. Oh, so maybe it is there, really. Okay, thanks.
Yeah. Okay, replication. All right, so here's our ambience. So one interesting thing about our ambience is that when our code is moving around or is inside of those ambients, it doesn't freeze, it doesn't stop executing. So if P can reduce to Q, then P enclosed in ambient N can reduce to Q enclosed in ambient N. So that's just saying that like these containers are really things that can be running the computations. So here's like a graphical depiction of what an ambient might be. So we have an ambient N, which has multiple parallel processes, P1 through PP. And then we also have these other ambients, these child ambients inside of N that are also running in parallel, M1 through MQ. So one of the things that we can do is, and so when we're reading this in m.p, this is sort of one process, and then this happened. So this is happening in parallel. It's not that action happens and both of these things are frozen beforehand. It's just like a precedence operator. But so when we say that, that confused me for a while. So when in process N we have something that says in m.p, and running in parallel we have another ambient m, a sibling ambient m, then it is instructing this whole ambient n to drive inside of m. So yeah, what our reduction is we have m with a child ambient n now, and in which p par q is running, and then it's that ambient is now running in parallel with whatever was running inside of m.
Yeah, an ambient is neither code nor data. It's like a container. So like in the persistent memory, they usually arrange it in a tree. And another good example, say, is, you know how Erlang VM works?
No.
They also arrange in tree structure as well. Just to help, if that helps people understand that.
Yeah, cool, thanks. And I haven't spent, yeah, a whole lot of time with this paper, so yeah, thanks for the other explanations.
I mean, they're all open to implementation decisions, right? You know.
Yeah, yeah. Okay, so the other thing we can do is, so we had that in operator, we have this out operator too, which this process P here is going to block until it exists inside of, its ambient exists inside of a parent ambient M. And then what it does is it just drives itself out, continues execution with P and whatever else was happening inside of ambient N. And now these are sibling ambients. And then we also have this open capability. So if we have a process running in parallel with an ambient, we can instruct the process to enter into, or we can instruct the process to sort of take whatever was running inside of Q and inside of the ambient M and rip it open and have it all running in the same ambient context. So note then that kind of like how we have object capabilities security by passing around names in Erlang, we have a similar notion here. So this process can't rip open the contents of container M if it doesn't know container M's name.
That's really helpful for me to see that. I was missing that detail before.
Mm-hmm. And so, right, you can construct these new names, and these new names are, you know, that operator really is going to give you a new name that is not constructible in any other way. Yeah, it gives you that unforgeable name. So once you have that unforgeable name, you can sort of decide what ambients have access to that name, what processes have access to that name. I guess what processes have access to the name, and then you also, yeah. So that was all I really had as an opening of the ambient calculus. I guess there was some more in chapter 3, some different operators, but I think that really covered the basics. Any other questions, or anyone else read further and think that there's something that I'm missing here?
So like if we go back to what Meredith was saying about how in Lambda, X was a meta variable and all these variables can just come out of nowhere. And in the row calculus, there's a better accounting of things because the names were kind of made out of processes and everything was built out of the zero.
Mm-hmm.
So is what Joshi was saying that this one is not quite as clean as row?
Mm-hmm. Yeah, this is as clean as pi is, right? So because we still have this notion of name, which is this set of things that we're pulling from, that we just, yeah.
Perfect. Thanks.
Yep. So one of the things that is sort of like troubling me is when we're saying define a new name in P, this is like a really interesting operator, because when you think about it, or when I'm thinking about it right now, and I might have the wrong intuition here, but this is assuming something about our names. This is assuming that we can construct a new name, that our set is that we are able to construct this unforgeable name, which sort of, I think, assumes something about our names themselves. We have to be able to do equality on names. We have to be able to do we have to be able to do like rewrites. We have to do substitution on names. This new operator is kind of interesting, because if you're thinking about it as like a Scala type, you're saying I want a new name to use in P. Really, the way that I'd want to think about it is you shouldn't have to supply a name to the type. You should just supply a process and say, I want a new name. So what I want this to return me is like a new syntactic element that I can sort of use inside of P that I can be guaranteed will have this unique name inside of it. It's a weird notion. And much cleaner in the row calculus.
When you say new, do you mean like NEW or NU? And
yeah, both. Yeah, both. The symbol V or the symbol new is sort of what's used because it really does mean new, like NEW.
Okay.
You can read this top line as new NNP.
I think you're right, Jake, but also new NEW isn't exactly like they call it a restriction. So it's not really, not necessarily constructing something new. It just says, you can think of it as if P has the name N, then ensure that it doesn't go beyond the scope of, sure, it can't be known outside of the scope of this construct. Is one way to see it. It's not necessarily creating a new thing, but simply a mask, a filter over P that doesn't allow N to be known.
Oh,
it could be passed out in the pi calculus, but it's also seen as just sort of a mask or a filter or something over P. Is the one way I see it, a restriction.
Yeah, no, that actually, I think that's a much better way to look at it. And I think I was getting too bogged down into sort of like, implementation details of how you would deal with this and how the like substitution would happen if, like, say you put it in parallel with something else that has the name, and like how do you actually deal with that? But yeah, no, that makes a lot of sense.
Glenn, do you think of that the same way in Rolang when we actually do, new X in this new scope I'm creating here?
Is there new in Rolang?
There's NEW. There's not this one. There's not the Greek new.
Oh, in Rolang.
Yeah.
I had some similar thoughts about that too. I'm like, oh, wait a minute. We have names that we construct. There are well-known names and that sort of things in, or blessed names, these things in Rolang. I don't know, Joshy. I don't know. Jake, do you have a thought on that?
Yeah, so I guess there's a couple of things. The new operator doesn't exist in row calculus, and that's because it can be constructed from the terms of the row calculus. And I'm not totally 100% certain about what that machinery looks like, but it's doable. So I think when we're saying new X in and then our process, that's what we're doing. It's just sort of syntactic sugar for whatever that expansion is. That is sort of equivalent to this construction, this masking type thing. But then you talk about how this actually gets implemented in Rolang, and that's sort of a different story. These things are given some sort of structure that's different than the thing that you are masking. And then you think of these like public names, which is sort of a different concept that is like a name given by the process that is a string. So this is just like they're introducing these new types that at a top level are semantically equivalent to the null process, but have some sort of other structure in them that you can manipulate and do fun things with. And that's not really related to this notion of new.
Well, and I would think in Erlang that there's a direct correlation to what shows up in the R space. I mean,
yeah.
That name you create is going to be the hand. Well, I think they may go through some manipulation because of alpha equivalence, but nonetheless, I'm pretty sure it maps directly to what's held in R space.
Yep. Totally. Okay. So yeah, that's the ambient calculus, or what I had on it. The blue calculus, I actually had a difficult time finding as good of a presentation. I found a blog post by Mike Stay, actually, written in 2008, which ended up being how I sort of learned what the basis of this might be. So the blue calculus sort of comes. It's this cool calculus that can be used to represent both the lambda calculus and the pi calculus. And the way it's sort of constructed is so you can think of this application of P to P in the lambda calculus as one way that you can execute lambda calculus is using this like lazy evaluation strategy where you only reduce a term if it's necessary to do so. But in the blue calculus, it's sort of like, I guess Mike Stay says it well when he says that builds the strategy into a language. So here's an example of application. So instead of applying one term to another term, it introduces this idea of these like reference names. So what we do instead is we say, okay, we're gonna apply P to some sort of name X, and we don't really know what's contained in that. This is like our reference pointer. And then in parallel, we have something that says that P prime, the thing that we're trying to apply to P, is what exists at that reference X. And so with those two things in parallel, and then also making sure that X is a new name, that's how our application takes place, is sort of through this like reference lookup. So yeah, here's a representation of the blue process calculus. You have a name, you have P applied to some name, you have this lambda term, which is similar. So these two things are kind of similar to what you have in the lambda calculus, modulo that like area of indirection. And then you have this new name concept that kind of comes from the pi calculus. And then you have this this P exists at X that are trying to dereference X and find what's there. You'll find a P. And then this X equals P is replication. That just means that there's infinite. So each time you access this reference, it gets consumed. So just like when you read on a name in pi calculus, if you read twice, and there's only one send, that second read will still be blocking. Same thing happens here. And then X equals P just means that we have infinite copies of P available at the reference X. And then that we have the parallel construction. So yeah, that's kind of a neat, like contains both lambda and the pi calculus. And an execution strategy for the lambda calculus. Anything that I missed there, or any questions? Oop, am I still connected? Are people there?
Yeah, all good.
Okay, all right, good. cool. All right, then I guess the last, kind of been through all of that. I haven't gone into much of the linear lambda calculus yet, but I'm thinking that'll be interesting. I'm hoping to explore that further. And then we had the grammar of the PyCalc definition. And I saw that Joshi worked on that a bit and got, pretty good representation of the grammar. But I thought I'd go over one of the things that I learned about these grammars. So let me share another portion of my screen here. Oh, weird, it's not allowing me to share. All right, are you viewing my screen?
Yes.
All right, is this readable?
Yes.
Okay, great, thanks. So say we have this language defined in KFramework. We have this expression language, and we can add things and multiply things. And I have this thing compiled. If say we have this statement here, 1 + 2 × 3. Our parser doesn't really know how to look at it. Doesn't know if it should look at it as a 1 + 2 × 3, or if it should look at it as a 1 + 2 × 3, because our grammar doesn't really specify what the order of precedence of these operators are. And so we can see that ambiguity if we try to cast, which is the take our definition of a K, a program expressed in a program that's expressed in K, and turn it into its AST representation. And if we give it the option -w all, warn all, we'll see that our parser encounters an ambiguity, and it doesn't really know what to parse first. So the way that we can fix this is in our grammar. And one of the things that it allows us to do when we're defining precedences is we can do something like this. So this says that in our abstract syntax tree, the times is sort of binding more closely than the plus. We can't have a direct node of times underneath or direct node of plus underneath a times node. So if we compile this, and then do the same, try to cast the same thing again, we'll see that the ambiguities will be removed. So no warnings this time. Well, one warning that we don't care about, but no parse ambiguity warnings. We still have a problem though with our precedence, and so now this is saying, what if we have 1 + 2 + 3? We're not strict in, we haven't told our parser how it should parse that. And so you can see that we get that parsing ambiguity. So if we, so what we can do for that is tell our K definition that our plus operation is left associative, and we'll need to do the same thing for our times operation. So now, oh, I gotta compile first.
So is left associative means it's going to do the 1 plus 2 before it adds the 3?
Yeah, that's how we'll parse it, at least. Yeah, so we haven't defined anything about the execution yet, right? So
Oh, yeah,
we might
okay,
want to
right.
erase that ambiguity in our execution. This is just, yeah, how it parses. So now we'll see. So now we'll see that that ambiguity has been resolved. And we can also just make sure that that our order of precedence, it is actually grouping things in the way that we want. We could try to read this ugly parse tokens that come out of cast, or okay, krun doesn't do that for us. So never mind. When it's chosen arbitrarily, so if you have that arbitrarily parsed thing, it will place under the construction it chooses, it will place parentheses around there when you're looking at it from krun. But I think since we've removed the ambiguity, it doesn't bother because it knows that we're going to look at this sort of how we've defined it. So yeah, you will have to actually look at the cast output. So let's look at that cast output a little bit more. And there's, yeah, we'll do that in a second. So exp. This way of defining our precedence works all well and fine as long as our language sort of, all of our precedences are sort of combined in this one expression. But say we have something like this, and then this rule exists here. And this can be add. So this doesn't mean the same thing when we're talking about our precedences. So compiling this. And then we get the parse ambiguity again. We should. Okay, I did it. Oh, yeah, so krun doesn't tell us that we have a parse ambiguity, but it does give us these parens. The cast command is what tells us we have the parse ambiguity. Oh, and then also, I guess we can supply to cast. We can tell it that our top level expression, we want it to be an exp. So it doesn't have to like determine which one it's looking for first, if it's looking for an exp or an add. But we see that the parse ambiguity is still there. So the way that we can fix that is we can have this syntax priority statement, and then tell it that well, we need to tell it that some rules have precedence over other rules. And the way that we need to do that is we need to give these rules labels. So we can, in the tag here, we can do klabel. This is mul. And then we can give this the klabel add. And then we can tell it here that mul is greater than add. And then we know that this doesn't work here, so we can just keep that how it is. And so now if we compile that, we'll see a couple of cool things. We'll see that when we cast our example that we won't have any parse ambiguities, and we'll see that it actually cleaned up our it cleaned up the representation in the cast. So up here we have this ugly like underscore plus underscore underscore exp syntax, and now that's replaced with this add token here. So we can read that what this really is doing is adding one thing, which is our 1, and then it's taking the multiply, which has precedence inside of it. It's multiplying 2 by 3, and that's in parentheses. So that's going to happen before this add takes place.
So the cleaner syntax tree happened because you gave it these K labels, add and mul?
Yeah. Yep. And yeah, it's just easier to read. It has the same meaning. And then just giving the labels also allowed us to do this, reference them here when we're talking about this syntax priority statement. So yeah, those are sort of all the constructions that you should need to be able to remove all the parse ambiguities in PyCalculus, the PyCalculus definition. I started reading up and working on the semantics and sort of just starting to scratch the surface of defining some sort of structural equivalence in the PyCalculus, and we can go over that next week. But yeah, you can.
Jake, I was going to ask: are we looking at just a tiny portion of the KFramework, or what we did there of sort of disambiguating the grammar and interpretation? Is that a tenth of the KFramework or half of it? What's your
I think it's a pretty small piece of KFramework. So where KFramework gets a lot more interesting is because we have like BNFC and other sort of grammar tools that it can be used to define and disambiguate grammar. I think the cool things that we saw are, one, it like showed us what our parse ambiguities were, and that like it showed us what all the options were, and then I think we get a lot more in depth into the meat of KFramework when we start talking about defining a computation and defining the semantics. So I think I've given a pretty good overview of defining a grammar. I think there's also some things that you can do that you can use, like rewrite rules to define like macros. So if you have like a basics of a grammar, you should be able to sort of extend that grammar with rewrite rules that rewrite without a computational step into your base grammar. If you're defining like higher order constructions in a language, I was looking at doing that to define some of like the shorthand for an input operation being shorthand for input.nil or output.nil, and then also was looking at maybe doing that for the to expand the notation that they have for sending multiple times on a name and receiving multiple times from the same name. That's in the PyCalc manual, but I haven't gotten that far yet, and it actually seems kind of inelegant, and I don't know if it's good to use that feature of that like macro definition in KFramework, or just to have that all in your syntax generically. It seems like the second option is better right now.
So I was trying to follow along with your EXP example, and what I had was one from last week where we had division and subtraction and some other stuff in there too. So if we want to set the precedence to disambiguate with all of those operators, how does that work? Because I don't want times to be greater precedence than divide, for example.
Yeah. So so what we can do, right, is we have divide. We can put that here. Now, what I don't know how to do yet is change the like associativity of a divide and mul operation. So if we have, right, like 1 plus or 1 times 2 divided by 3, I don't really know how to remove that parse ambiguity yet without and like tell it that I want these operations to be read from left to right. It looks like the cast parser automatically chooses the first, so it automatically goes left from right when things are of the same precedence. But I'd like to be able to tell it that that isn't an ambiguity, that that's how I want KFramework to parse my statements. But yeah, I don't know how we do that yet.
Okay. Okay, cool.
But it does allow this notion of like these are both the same, and you have this. So another interesting thing too is if like you tried to so if you tried to do, oh no, that would be okay. Yeah, right, because this should still work. Yeah, there's, let me see if I can find my, I don't remember. There was a way that I could get it to not parse the program due to like the only valid way to parse it would be if without parens the one construction had precedence over another, which was the opposite of how I defined it in a file. And I had some example PyCalc program that would do that, and then it would fail to parse because of the order of precedence. But yeah, I can't find that right now. Cool. Okay. Yeah, that's all I have for this week.
Thanks, Jake.
Yeah, thank you. Yeah, and Ryan, unfortunately, yeah, I saw the same thing, that a lot of the links on the Blue Calc page were dead. Yeah, which is why I found that Mike Stay article. But, all right. See you later.
All right. Thanks a lot. See you guys in a week.
Bye.